Okay, so we're continuing with this hemophilia cross, where we have our unaffected mom, but our affected dad. And we're going to see how this inheritance plays out. So, like we did before, we would have this X chromosome for mom would pass into the two boxes below, showing us that, it has a 50% chance of being included in the offspring options. Same thing with this second X chromosome of hers, with that dominant allele. Now we're going to do the same thing with dad's. We have both of our H's, both of our X's up top with the little h, and then we have his y. Okay. Looking at this cross, we can see that both of our females have a big dominant allele and a little recessive allele. That makes both of these carriers. Both of these down here have the dominant H allele. So, looking at this, 100% of the offspring would actually be unaffected. Oh, and that's going to be really difficult to write, so we're going to stop it here. But unaffected, okay? They are not going to have hemophilia. So what if I do another Punnett square, and we change it up a little bit? Oops. Okay, so that might throw off the boxes just a smidge, but hopefully it won't be too bad. Oh, I can get rid of that one. Okay. So, what if mom is a carrier? She has one dominant allele and one recessive allele. But dad's not a carrier. Okay, so dad is not going to have hemophilia. In fact, neither of these parents have hemophilia, right? Because mom's just a carrier. She's still unaffected. She would need two of these recessive alleles. And dad is dominant, so he doesn't have the hemophilia allele. So when we write in our genotype here for each of our kids, for their sex chromosomes, we see that the first two that I made here, they are unaffected. Okay, so mom and dad passed on their unaffected alleles. And same thing here, mama passed on the unaffected allele to her son. But things start to change a little over here with mom's affected allele. So mom doesn't have hemophilia, but she can have a kid who does. Okay, and that kid is her son. Remember, because males have only one X chromosome, all it takes is for them to get one copy of that recessive allele, and they'll have the disorder. So this individual, this son, has hemophilia. Now his sister, potential sister, also got that allele, but she has a dominant allele acting as a safeguard. She's just a carrier. Okay, so sister is a carrier, but the son has, or brother, has hemophilia. So hopefully walking through this, we're able to see what it means to have a X-linked recessive trait. Okay, I'm going to clear that. And let's move on to talking about X-linked dominant. Okay, so looking at an X-linked dominant trait, for that, all you need is just one, I had to think about that, just one of the what's considered dominant allele. Okay, with one, you'll have the disorder. So let's look at this left-hand side here. We can see that mom is affected. Okay, she has the disorder. And dad, he's unaffected. He doesn't have the disorder. Now, some of you might say, well, why does she have the disorder if she has an allele that's unaffected? So she has one affected allele in blue, one unaffected allele in white. And that's because this is an X-linked dominant trait. Okay? So that doesn't matter. You just need one copy of that dominant allele, and you will end up having the disorder. So let's look at the offspring. Mom passed on her affected allele to both her daughter and son here, and she also passed on her unaffected allele to a daughter and a son. So just looking at this, she has a 50% chance of passing on that disorder to her offspring. Okay, because 2 out of 4 options would lead to having an affected daughter or son. So I said earlier that this is something that can happen more in females than in males. This example doesn't exactly show that, but the next one does. Because the reasoning for these X-linked dominant disorders happening more in females is because they have 2 X chromosomes. Okay, so based off of probability, if you only need one of the X-linked traits to have the disorder, and you happen to have 2 X chromosomes, you have a higher chance of actually getting the disorder. And we can see that here with this kind of cross. So we have the dad is affected. If he has the disorder, he's going to pass that trait on to every single daughter that him and his wife have. Okay, and that's because his X chromosome, his affected X chromosome, gets passed on to both of the daughters that are produced. Okay, so there are no more carriers. It's an X-linked dominant trait. So both of these daughters got a copy, and they're going to get his disorder. So here's a specific disorder called Fragile X syndrome, and this is again, X-linked dominant disorder, and it results in mild to moderate intellectual debility, and actually some differing, like, physical characteristics. So, larger ears and a longer face. And this is typically found more in females. So we can see down here that, again, I mapped this out using H's. Big H as being dominant, little h as being recessive. And females only need to get one affected copy of that H allele, dominant allele, and they will have the disorder of Fragile X. The only way to be unaffected and not have the disorder is to get two recessive alleles. Same thing with males. It doesn't matter that they only have one X. They just need that one copy and they'll have it. But they only need one copy to not have it. Okay, females need to have two copies to not have an X-linked dominant disorder. Males only need to not have one copy. Okay, so for this, we can go through another test cross. And we're going to map out basically what we just saw with those kind of what we would call a pedigree image, where you're looking at a kind of like family tree. So here is a Punnett square. And I said that we would be looking at an unaffected mom. So mom has both of the recessive alleles. Remember, if she had one dominant, she would be affected and have the disorder. But she doesn't have the disorder. So we know that both of these are recessive. Dad, on the other hand, has the affected allele. Okay, so he has the dominant. So now we're going to look at that pattern of inheritance. So we have Dad's affected allele being passed on to two of his offspring, and his Y chromosome being passed on. And here we have Mom's, all of Mom's unaffected alleles on her X chromosomes. So this is going to be a little backwards, but hopefully you get the drift. So we can see here that both sons have the little h alleles, so they are unaffected. Okay, they will not have the disorder. But both of these females got a copy of that affected allele. Okay, and because of that, they're going to have the disorder. So here we have 100% of the females have Fragile X. Just do F for female. 0% of the males would have Fragile X. So again, another difference in the probability that we'll see, which is why this is categorized as non-Mendelian inheritance.